So this question asks us to find our derivative using the limit definition. We now know the power rule, so we can apply that. So let's just go ahead and apply the power rule before we throw in the limit definition to see what happens. So let me change over my pen if it'll let me. If we look at this, we can see we have a exponent of 2, we have an exponent of 1. If we really wanted to, we could even add, as Stan pointed out, our x to the 0 here. So if we apply the power rule for each of these pieces, we know the constant's just going to pull out in front. We can use that almost thinking about our limit definition and our limit laws that we saw back in the last unit, right? That constant multiple, we could just pull out in front of the limit, evaluate the limit, and then multiply by our constant. So same business here. I'm going to pull the 4. And then I'm going to deal with that x squared. So the 2 comes down in front, and then we have a 2 minus 1. I'll do it slow for our exponent. We did this next term. We got 3. I'm going to, again, be very slow about it. I'm going to pull the 1 down in front, and then make this x to the 0. And the last one, I'll pull the 0 down in front. And then if you really wanted to, I guess, oh, I forgot to do the 1 minus 1. And I'm just doing this because when we saw all those definitions, sure enough, we were given a rule for a constant. We were given a rule for just x. And Stan pointed out that really those rules all come down to the power rule. If we just have that one rule, our power rule, we would be able to have all of it. None of them were anything different. It applied for all of them. So let's just go ahead and put our power rule here off to the side. We'll use the other notation. I'll be good about it. We have dy dx of x sub n is equal to n x to the n minus 1. Cool. So that's our power rule. So we could apply it for a couple of cases and then see what happens. But we know what our answer should be. If you clean all of this up, we should end up with 8x plus 3. And this is something you will get very good at, I promise. So this is what we should end up with if we do all the limit definition stuff correctly. This is why I said that quiz from Monday gets easier over time because you know what you're supposed to get out and you can kind of find your errors knowing what your answer should be. So our limit definition, we're using that second definition, the limit as h goes to 0, because that's going to get me an f prime of x and not just the derivative at a point. And we need it to be f of x plus h minus f of x all over h. So the first thing we got to do is figure out our f of x plus h. So we're going to plug in x plus h everywhere that x appeared in our original function. So our original function had 2 x's, ignoring that x to the 0. And so we're going to plug in x plus h for both of those using some parentheses and making sure we aren't screwing anything up here. So we have 4x plus h squared plus 3x plus h, still in some parentheses. Pen is being very laggy. Minus 7. Nothing to plug into on that last term, so it just stays there as a 7. So all I have done is this portion of my difference quotient, the f of x plus h. And I am going to suffer and do this all inside of the difference quotient just so you can really see the format. Now this is all subtracted by our entire f of x. So I'm going to go ahead and put some parentheses around the entire thing. We get a 4x squared plus 3x minus 7. Cool. And this is all over h. So again, I'll highlight some stuff so you can see where it's coming from. This entire thing in the parentheses is just my entire f of x, the entire function we are doing this with. Of course, without the random addition of x to the 1 and x to the 0. So now is when the algebra comes in and a lot of bookkeeping, right? This is the mix. It looks impressive because we use a lot of space, but at the same time, it's not really impressive math. It's just a lot of places to lose a negative or a coefficient or something. So if we were to distribute out this first term, we'd end up with an x squared plus 2xh plus h squared. Now there's a 4 out in front, so I'm going to go ahead and multiply these all by 4. Boom. Ugh, I made that one too close. Let's give myself space, and I forgot. Plus 4. Okay, and then we keep moving. We'll distribute the 3 out. 3x plus 3h minus 7. So all I have done is expand out everything in that first thing, that f of x plus h. And I'm going to go ahead and distribute the negative sign to all of the terms in my f of x. So it'll become a minus 3x and a plus 7. And this is still all over h. So all I've done is clean things up a little bit. And now I'm going to look for all this stuff that cancels, right? Magic's going to happen here. We still have a limit. Oh my gosh, I forgot my limit. You guys should have been yelling at the camera, at the screen. Limit as h goes to 0. But now what should happen is a bunch of things should cancel, and we should be left with stuff that we can factor an h out of so that we don't have our 0 over 0. Because right now if we were to plug in, we'd have 0 over 0. So let's go ahead and look around. Minus 4x squared and 4x squared by 3x minus 3x by minus 7 and plus 7, adios. So we can see all of the terms that we have left have an h in them. So we can factor that h out or divide the h from each term, however you want to think about it. But now we are at this stage. The limit as h goes to 0 of 8x plus 4h plus 3. And now that we don't have 0 over 0, we can plug in. We can do direct substitution with that h of 0, and we end up with 8x plus 3, which is what we knew we would get using the power rule. So we know that we have done everything correct, and we are on our way. I'll do one more example with something that is beefier. Actually, maybe I'll do 2 more. Might as well see our radical and our rationals, so we see something beyond just our polynomial version of it.